Okay, so before I jump into 6.3, I just wanted to do a couple of review problems from 6.1 and 6.2. So just because this chapter is kind of long, and the stuff from 6.1 and 6.2 doesn't really carry forward so much. So let me make up some functions. Call one f of x. So here are two functions. Now first I want to go find g composed with f of x, and then I'm going to do a second problem, find f minus g of 2, and then find the inverse of g. So three problems. The first two problems were the kinds of problems we saw in section 6.1. The third problem is the kind of problem we saw in 6.2. So to do g composed with f of x, I have to replace any x, or the x, in the g function, because it's written first, with the right side of the f function, the thing that's written after the open circle. And then I'm going to simplify. To do these composition of functions, you need parentheses. So here, g composed with f of x, I'm going to go 5, and then I'm going to replace the x with x squared plus 3x minus 4, and I still have the 5 and the plus 7 part of the g function. So that is what g composed with f of x is unsimplified. So if you got that far in the test, you definitely get some partial credit if this was the test question. I'm going to clear the parentheses that I put in, going 5 times x squared is 5x squared, 5 times 3x is plus 15x, 5 times minus 4 is minus 20, parentheses gone, still have the plus 7. The minus 20 and positive 7 can be combined to a minus 13. So I'm going to get g composed with f of x equals to 5x squared plus 15x minus 13. It definitely would be wrong to use the quadratic formula now to solve for x. It definitely would be wrong to multiply by x. What I might do off to the side is try to factor, because the problem didn't start factored, so I'm going to attempt to factor that my answer, my 5x squared plus 15x minus 13. I'm going to use bottoms up. I'm going to start off by multiplying the 5 and the minus 13, which is going to give me x squared plus 15x minus 65. And then I know that my signs are plus and minus, so that I'm subtracting to get the 15. The factors of 65 that I have to choose from are 1 and 65. 2 doesn't go into it, 3 doesn't go into it, 4 doesn't go into it, 5 goes into it. It's 5 and, I guess, 13. 6 doesn't go into it, 7 doesn't, 8 doesn't, 9 doesn't, 10 doesn't. I think I'm done. These are all the factors of 65 that I can think of, and there aren't a pair of factors that I could put in the lasts that subtract to be the 15. So because this is prime, I'm done with this, and I have a correct answer. And that's all there is to do for the first review problem, similar to something from section 6.1. The second review problem, it says f minus g of 2. When we did that, those kinds of problems in section 6.1, we started off pretending the problem had an x, and had this problem had an x instead of the 2, what I would have done is put a minus sign followed by a parentheses. To the left of the minus sign, I'd put the right side of the f function, which is x squared plus 3x minus 4. after the minus sign inside the parentheses, I put the right side of the g function, which is 5x plus 7. Turns out that I really don't have to simplify that for this particular problem. At some point, I need to change the x to 2, and I need to simplify. It's probably, for me, easier to change the x to 2 before I simplify than it is to simplify with the x's. So to get the answer to this problem, you barely could read that. That's a plus. This is a minus 5 times 2 plus 7. So I'm going to do this in my head, but you can do it on your calculator. Do the parentheses first. The parentheses is minus 10 plus 7, which is going to be minus 17. So the parentheses part, after I get the parentheses down to one number, I can just make it a minus 17. And then the 2 squared part is a 4. The 3 times 2 part is a 6. So I get 4 plus 6 minus 4 minus 17. And I can do that without my calculator because the 4's cancel. I'm left with 6 minus 17, which is negative 11. So for an answer, so again, this was the answer. Oops. This right here was the answer to the first problem. And then for the answer to this problem, I'm going to say f minus g of x equals negative 11. If I wanted to, I could have done this whole thing on my calculator and still got that negative 11. I could have just did parentheses 2 squared plus 3 times 2 minus 4 minus parentheses 5 times 2 plus 7 and my parentheses. So it gives me the same minus 11. I don't care if you do it by hand or use your calculator. So that's 2 of the 3 review problems I wanted to do. The last review problem is from section 5.2. I want to find the inverse of g of x equals 5x plus 7. To find an inverse of a one-to-one function that's written in function notation, so I'm going to find the inverse of g of x equal to 5x plus 7. The steps that we do is first we change the function symbol to the letter y. So we write this as y equals to 5x plus 7. And then I actually create the inverse by switching the x and the y. I get x equals 5y plus 7. Then I do the algebra to solve for y. To solve for y, I'm going to minus 7 and get x minus 7 equals 5y. And then divide everything by 5 and get x over 5 minus 7 over 5 equals to y. I could have written 1/5 x minus 7 over 5 equal to y, so if you wrote that, that would be okay. So I'm basically done. Now I just need to write my answer using the inverse notation. Or inverse symbol if you want. Notation and symbol I might use interchangeably here. The inverse symbol is the same letter as the function with a little -1 exponent. So I'm going to say the inverse of g of x, and that's how I'd read that when I see that symbol. I wouldn't say g to the -1 power. With function notation, that negative exponent means inverse, and then whichever of the two answers you decided to come up with. So you could have the 1/5 x in there just as well. And that's everything for that problem. So I know there's a few more things that might be test-worthy from section 6.2, but these are the kinds of things that I'd ask on a test from 6.1. This is definitely something I'd ask on a test from 6.2. 6.3 isn't a super long section, and the nice thing is a lot of it I could do on my calculator. So problems 1 through 6 says evaluate, use a calculator if you need it. I don't need a calculator for any of these, but if you need a calculator for all of these, it's okay. And if you're going on to the calculus sequence, Calc 1, Calc 2, Calc 3, or even brief calculus, you should not be relying on your calculator to do these. If Math 151 or 142 is where you're ending your mathematics studies, and then it's okay not to be able to do these by hand. But I'll do them all by hand, and I'll come back and do them on my calculator. The first two problems I see from this section have negative exponents. I remember that negative exponents, when they're not involved with function notations, usually turn into fractions. 5 to the negative 3 can be written as 1 over 5 cubed, and I know that 5 cubed is 125. So my calculator should give me that when I do this. When I go 5, up arrow, negative 3, well, and do it right, if I go 5, up arrow, negative 3, my calculator tells me that it's 1 over 125, but I knew that anyways. 4 isn't really any different than 2. By hand, I'm going to write it with a positive exponent. It's going to be 1 over 8 squared, and I know that 8 squared is 8 times 8, which is 64. The answer to part 4 should be 1 over 64. Again, on my calculator, I could just go 8 exponent negative 2, and my calculator will tell me that's 1 over 64. 6 to do this by hand. This is the cube root of 64 squared. By hand, first, I'm going to find the cube root of 64, and that's 4, because the cube root of 64 asks the question, what number times itself 3 times is 64? That's going to be 4. I haven't done the squaring yet, so now I'm going to square, and 4 squared is 4 times 4, which is 16. So again, if you're going to Calc 1, Calc 2, Calc 3, this should almost be effortless for you at this point. Calc 1, Calc 2, and Calc 3, they're not really that hard if you're really good with symbolic manipulation. If you do algebra just amazingly well, you can manipulate x's and solve things in your head, and if your algebra skills are really, really, really competent, really good, then you'll do calculus won't be bad, because calculus itself isn't that hard. It's the algebra within calculus that's just going to make your head spin a little bit if you're not really, really gifted or comfortable with the algebra from Math 120 and 151. So on my calculator, 64, up arrow, fraction 2 over 3, and I get that same 16. So those problems were, in some sense, effortless for me. Similarly, the next few problems are going to be kind of effortless for me. For these problems, my calculator, when I do them, it's going to give me a nasty decimal. And generally, if my calculator produces a fraction or an integer for an answer, that means there's a way to do them without my calculator that isn't that impressive. When my calculator comes back with a decimal answer, that means it's probably likely, well beyond a normal person's ability to do them without a calculator. That would definitely be the case for each of these 3 problems. I have little hope of doing these without my calculator. So my instruction says use your calculator and round to 3 decimals, so I know all of these are going to have lovely decimals. So first one, 3 to the 2.26 power, and I get, my calculator tells me this is 11.9755. Since I'm rounding to 3 decimal places, I need to look at the number in the 4th decimal place. The number in the 4th decimal place is 5 or larger. I round the 3rd decimal up. So for my answer, that 5 in the 3rd decimal place is going to be round up to a 6. So for an answer, I'm going to say this is approximately, I'll write a squiggly equal as opposed to a nice straight equal sign. If I wrote a straight equals, that means they're perfectly equal. If I write a squiggly equal sign, it means it's rounded. Since this is a rounded answer, these are approximately the same. They're not exactly the same. It's nicer to use a squiggly equal, but I won't take points off if you don't. If you do, use the wrong equal sign. So 5 to the square root of 2 next is 9.7385. I don't care anything after the 4th decimal. Same issue here. The number in the 4th decimal place tells me to round the 3rd decimal up. Since I'm only asked for 3 decimals in my answer, I have to decide if the 3rd decimal is going to remain at 8 or if it's going to round up to 9. I look at the number after the 8. If it's 5 or bigger, I round it up to a 9. If it's 4 or less, I leave it an 8. I'm going to round it up again. And then the last one of these, 2 exponent negative square root of 3, I get 0.3010. So 0.3010. The 0 to the left of the decimal you don't really have to write, but it's kind of nice to write it, but it's not necessary. The 1 in the third decimal place, I'm not going to change to a 2 because the number after it isn't big enough to force me to round it up. So for this, you could write 0.301, or you could write just 0.301. It's not necessary to write a 0 to the left of a decimal point, but it's customary because if you just write a decimal and then a decimal number without the 0 in front, if I read it quickly enough and if I write my decimal small enough, I might think that's 301. Writing a 0 first and then the decimal makes the decimal stand out. Each of the first 12 problems, this material that I wrote, I don't know, I probably wrote it like in 2008, maybe 2009, and back in 2008, 2009, the calculators that I used to do these, it was a fight, to say the least. So these problems, had I written this stuff this year, I might have not even had them in there because this calculator makes these problems kind of effortless. The next few problems are graphing problems. I call these graphing exponential functions. They're exponential functions because the x is in the exponent. So I call these exponential. Anytime an x is in an exponent, you have an exponential problem. I'll call this a function because the graph is going to pass the vertical line test. For exponential functions, when the exponent is just x, I use the -21012 table. So when the exponent is only x, I use this table, -2, -1, 0, 1, 2. I'm going to do this table by hand, and then I'm going to do it on my calculator just to show you what my calculator is doing for me, because it shouldn't be mystifying what your calculator is doing. It's not doing anything you couldn't do by hand. So to plug -2 in for x, I'd go g of -2 equals 2 to the -2 power. I know that 2 to the -2 power is 1 over 2 squared, which is 1/4. Putting 1/4 here is absolutely perfect. My calculator, I think, is going to put 0.25 instead of 1/4 because that's the decimal equivalence of 1/4. And when I go to plot that point is just a little bit above the x-axis over at -2 on the y-axis. For g of -1, I'm going to go 2 to the -1 power is 1 over 2 to the first, which is 1/2. And again, my calculator, when I have it do the table, it will probably give me 0.50, which is the decimal equivalent of 1/2. And that point's a little bit higher, so I'm going to go to -1 on the x-axis and then up halfway between 0 and 1. I might have went a little bit too high, but it's okay that I overdid it a little bit. Third one, g to the 0, I'm going to go 2 to the 0 power. Anything to the 0 power is 1. My calculator will give me exactly that 1, and I'll plot that point here. And then the last one, second to last one, g to the 1 is 2 to the first power. 2 to the first power is just 2. That's going to give me the 0.12. Now the last one I'm going to do, g to the second power equals 2 squared, and 2 squared is 4. That for me is enough to complete a graph. Because it's our very first graph, I'm going to do 2 extra points. I'm going to do a -3 just as a bonus. G to the -3 power is 2 to the -3, which is 1 over 2 cubed, which is 1/8. And my calculator for 1/8 knows that its decimal is 0.125. And that point is barely above the x-axis, but 0.125 is positive, so when I get to -3 on the x-axis, I still have to go up. And let me just squeeze in g of 3 down here. G of 3 is 2 cubed, 2 cubed is 8, and then 3/8 is up here. So now I can really see a good connection, graph that I'm going to connect. Exponential graphs generally don't go beneath the x-axis. So this graph off to the right, it's going to get really high really quickly, but off to the left, each successive point is going to get closer and closer to the x-axis, but the graph is never actually even going to touch the x-axis. It's always going to be microscopically above the x-axis because the y's are always going to be positive. So I actually plotted 7 points and sketched a graph. Let me show you how to get the points on your calculator, because we already know how to do this, but let's do it again anyway. So on my calculator to get this table, I go mode, table, f of x is 2, up arrow, alpha, x, start at, I'll even do -3, start at -3, end at 3, step 1. So you can see all my points. So there's the -3.125, the -2.25, the -1.5, the 0, 1, the 1, 2, the 2, 4, and the 3, 8. I'm very fine with you using your calculator to get the y values, because it's not that hard to do by hand. It's just time consuming to do by hand. So this would be a nice solution for problem 14. The key to most successful graphing is getting a good starting group of x's. If you don't get a good starting group of x's, then the points that you get might not point you in the right direction for the graph. This is a very typical exponential function. Mostly they look like this, where on one side they flatten out and start touching the x-axis, but they're barely above the x-axis, and the other side they shoot up real high. Sometimes the graph is reversed, where it gets real high on the left side and on the right side starts approaching the x-axis. So we need to come up with a strategy to figure out what my table should be. And the first thing for these problems, if the exponent is only x, then the -2, -1, 0, 1, 2 table will work just fine. If you want to extend it from -3 to 3 to get a couple more points, that's also okay, but it's more than you need. I'm only asking for 5 points. So for this problem, even though the base is much more complicated, 1/2 to the x and 2 to the x, what they have in common is they both have the exponent as just x. When the exponent is just x, this -2, 1, 0, 1, 2 table is completely fine. So for this problem, I won't even do the full table. I'm just going to do -2, -1, 0, 1, and 2. I'll do a couple of points by hand, and I'm going to use my calculator to get the rest. If I wanted to do this k of -2, I'd go k of -2 equals 1/2 to the -2 power. Then I'd have to remember from chapter 4, if we have a negative exponent outside a fraction, I can make that negative exponent by taking the reciprocal of the fraction. So this is going to give me 2/1 squared, which is the same as 2 squared, which is going to be 4. If I did k of -1 by hand, this would be 1/2 to the -1 power, which is 2/1 to the first power, which is the same as 2 to the first power, which is 2. I could, if I wanted to, do every single y by hand. I don't want to, so I'm going to use my calculator. So mode 7 parentheses fraction 1/2 parentheses exponent alpha x, start at -2, end at +2, step 1. And now you see there's my -2 comma 4, there's my -1 comma 2. Anything to the 0 power is 1, so there, that next point I could have gotten easily by hand. The next two would have been a little bit harder by hand, but it wouldn't have been impossible. In fact, it wouldn't even been that hard. So those are the points I'm going to plot. Let me just show you how this one would have worked by hand. This one, if I did k of 1, that would be 1/2 to the first power. Anything to the first power is itself, so I'd get 1/2 by hand, which my calculator gives me 0.5 for. So it's an adequate table. My calculator is just saving me some busy work for the most part. So let me plot the points. I get the point -2, comma 4, -1, comma 2, 0, 1, 1 and 1/2, 2 and 1/4. If I made more points, I would have had a -3 and 8 and a +3 and 1/8. This graph is kind of the opposite of my, and in fact, let me just extend this table. I'm going to do -3 and +3. Let me do the same function, and just extend the table for you so you can see what the other points that I'm not showing you, what I'm saying they are anyways, what they would look like. So 1/2 to the x, start at -3, end at 3, step 1. So here's the point -3, 8, which would be up here, and the very bottom point would be, whoops, really? Did I mess up? I don't know. Let me see. Messed up somehow. Mode 7, parentheses, fraction 1/2, parentheses, up arrow, alpha, x, start at -3, end at +3, step 1. I don't know what I did wrong, or if I did anything wrong. There's the point -3, 8, -2, 4, -1, 2, 0, 1, 1.5, 2.25, 3, 0.125, which is 1/8. And the fourth, if I plotted that point would be closer to the x-axis than the other decimal points, because 1/8 or 0.125 is closer to 0, which is what the x-axis is, than the other 0.25 and 0.5. So this graph is the backwards image of the last graph, in that on the left side it shoots up and gets really high really quick. It goes all the way up to positive infinity. But on the right side, the graph actually is always slightly above the x-axis and shouldn't really even touch the x-axis, because the y's are always going to be positive, something slightly bigger than 0, something slightly above the x-axis. My ink, my pen writes so widely that it makes it look like the graph touches the x-axis. Is actually microscopically above the x-axis, but for our purposes, this is a completely adequate graph. So what the first two problems had in common is they just had x for an exponent, and when you have just x for an exponent, the -2, 1, 0, 1, 2 table is perfect. When the exponents get more complicated, we treat the exponent like a parentheses in a parabola problem. So I see an x minus 4. What I'm going to do is just like I seen if I would have saw an x minus 4 in a parentheses in a parabola problem. And in a parabola problem, if I saw an x minus 4 in a parentheses, I would change the sign of that x minus 4 to a +4 and find some numbers on either side of that 4. So I'm going to use the table 2, 3, 4, 5, and 6 for this problem. The surprising, well, it won't be so surprising. This would be the perfect table for this. So if the exponent is just x, like it was in the first two problems, the -2 to 2 table is perfect. If the exponent has a plus or a minus in it, then I change the sign of the number in the exponent and do the table just like a parentheses parabola problem. Get all these y's by hand. I'm going to get some decimals that I'm not as familiar with, but I can deal with them. So mode 7, 3, exponent alpha x minus 4. This table start at 2, end at 6, step 1. What the? Okay. I don't know if I must have entered something wrong again, because that is, that's okay. So at 2, I get 0.1111, which is actually 1/9. So this is 0.1111. At 3, I'm at 0.3333, which is actually 1/3. At 4, I'm at 1. At 5, I'm at 3. And at 6, I'm at 9. So I can get a decent shot at this table now. If I was doing this by hand, if I was doing, if I plugged the 2 in and did m of 2, I'd go 3 to the 2 minus 4, which is 3 to the -2 power, which is 1/3 squared, which is 1/9, and 1/9 and 0.111 have the same decimal equivalent. If on my calculator I did fraction 1/9 and then hit the SD button, it gives me 0.1 with a bar on it. Repeating means 0.1111. So it's a little bit harder to plot this point. I'm going to go over 2 and up 0.111. That's kind of 1/10 of the way up between 0 and 1, so it's really close to the x-axis. So the 2 and 0.1 I'm going to put about there. That's probably even a little high. And then the 3 and 0.3, that's less than halfway. I made it a little bit more than halfway just because I don't have a lot of control with this fat pen. And I didn't even plot it right. That's not good. Let me do it on this paper then, because I don't like the way I plotted that. So the points I need to plot are 2 and 0.1111. That is really, really close to the x-axis. And 3 and 0.333, that's 1/3 of the way, less than halfway. So I tried to make it less than halfway. And then 4 and 1, 5 and 3, and 6 and 9. So what this one does is it gets really high, really fast going off to the right, and then going off to the left, kind of like the first problem. It's always going to stay above the x-axis. It's never going to dip under the x-axis. So that's problem 18. M of x equals 3 to the x minus 4. It's never going to dip under the x-axis, and it goes on forever off to the left. It will almost look like a horizontal line when it goes off to the left because it becomes so flat. But off to the right, it goes up to infinity. Thank gosh for my calculator here, because it's an unpleasant one to do by hand a little bit. So again, I look to the exponent. There's a -1. I'm going to change that -1 to +1. I'm going to go to the left 2 and to the right 2 to figure out my starting table. So when your exponent, you treat like a parentheses in the parabola problems. You change the sign of the exponent, the number in the exponent. I change it from negative to +1. The table I'm going to use is -1, 0, 1, 2, 3. And I'm going to do this by hand now, or with my calculator, should I say. Mode 7, parentheses, fraction, 1/2, parentheses, exponent, alpha x minus 1. Start at -1, end at 3. Oh, I can tell what I did wrong. Go backwards. End at 3, step 1. And then it tells me at -1 I'm at +4, at 0 I'm at +2, at 1 I'm at 1, at 2 I'm at 0.5, and at 3 I'm at 1/4. Plot the points, connect them, make my graph. So -1, +4, 0, 2, 1, 1, 2 1/2, 3 1/4. So the best I can, I'm going to connect these. And this one, because the base is a fraction, it goes down on the right and up on the left. Generally, if the base is bigger than 1, it goes up on the right, down on the left. If the base is less than 1 or in between 0 and 1, it looks like this. Okay, so that's the algebra part of this. The rest of it, the section, is word problems. And they're not the worst word problems. They're easier than the word problems that we've had recently. And in this section, if you want to, I've never asked something like 24 nor 26 on a test. I always ask problems like 27 through 30. So if you're not wanting to bog your mind down with something that's not going to be on the test, you can be comfortable that 24 and 26 aren't on the test. Every word problem in this section, somewhere in the word problem, there's an equation and it explains the equation. The real nice thing about these word problems is to get from the question to the answer, we just have to plug a number into the equation. So there's some distractors in problem 24. It talks about there's a colony of 2 million bacteria growing in a medium. The population after t hours is given by the function. So this function, p of t, this stands for the population, or the number of bacteria, and then equals 2 million times 2.3 to the t. This stands for the number of hours. that the culture's been growing. The 2 million in the formula is that 2 million. So what this formula can tell me is if you tell me how long the population's been growing, I can approximate how many bacteria are in the population by just plugging that number in for t. And that's all I have to do. This says find the population after 12 hours. All I'm going to do is put 12 in for the hours, and the hours stand for t here. It's the time. So to solve problem 24, this is exactly what this formula does. If you tell me how many hours the culture's been alive, I can approximate how many bacteria are in it by plugging in that number for t. So for problem 24, if I plug a 12 in for t, this says the population after 12 hours equals 2 million times 2.3 to the 12th power. I'm going to do that on my calculator. Mode 2 for complex. I probably don't need to be in complex, but it's okay. I'm going to do this on my calculator. I'm going to do 2 million times parentheses 2.3 exponent 12. And that's going to give me the population after 12 hours. Oh, and I get this lovely notation. This is good because this is new for me on this calculator this semester. 4.382924886 times 10 to the 10th. For those of you in chemistry, you might understand that this is scientific notation. In scientific notation, maybe fine for a chemistry class. I guess it's fine for a math class. I'm going to take this out of scientific notation. This is a number that's fine, but I'm going to make it better. I'm going to get it out of scientific notation by moving the decimal 10 places to the right. So I'm going to take the decimal and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That 10th move, I don't have a number there, so I need to put a 0 in. So the number of bacteria in this population are going to be 4, 3, 8, 2, 9, 2, 4, 8, 8, 6, 0. So comma, comma, comma. So 43,829,248,860 bacteria. I shouldn't have that gap between the 2 and the 4 there, but it just happened. So this is the answer. That's how many bacteria. So we started off with 2 million bacteria, and after 12 hours we have 43 billion bacteria. Again, 24, although it's a friendly, easy problem, it's not going to be on your test, nor will 26. 26 is going to be similar in that in the question there is a formula, and it talks about radioactive material decaying, and over time you start losing material. It just decays, it disappears, or it goes back into nature. It says this formula tells me what amount of 500 grams is going to be left after t years. The T stands for the number of years. The A, it doesn't say so well, but it's the amount of material that's left after so many years. The 500 there is the beginning amount of material. In 10 years, I'm going to have less than 500 grams because it's decaying, it's going down. How much do I have left in 10 years? This 10 stands for years, which is T. So the amount of bacteria or radioactive material I'm going to have in 10 years can be found by plugging 10 into the formula for T, and it's breaking out in my calculator, and it says round to the nearest 10. So I'm going to go 500 parentheses fraction 2/3 parentheses exponent 10, and I get, it says round to 1/10 of a gram, so I'm rounding to 1 decimal. In 2 decimals I get 8.67, so there's going to be 8.7 grams left after 10 years. So it started with 500 grams and it's decaying rapidly, and after 10 years there's going to be 8.7 grams left. So those two word problems aren't test worthy, but the money problems are test worthy. And before doing the money problems, which are easy, I want to help you understand compound interest by making a problem up that's like the original problem, but I'm going to do it by hand. So I'm going to make up, this is a made up problem, just to help you understand compound interest. I'm going to do it with a table, and then I'll show you how to use the formula and explain the formula. So I'm going to do this. An initial deposit of, let's do a lot of money, $10,000 earns 8% interest compounded, I'll do the hard one, quarterly. How much will be in the account after 1 year? So this isn't one of the homework problems, but it's something I can do easily. I'm going to write the formula up here because I'm going to leave this. I'm going to cover up the formula in a second. So the formula that eventually I'm going to use is this formula. So ultimately, when I solve the money word problems in this section, I'm going to use this formula, A equals P times 1 plus R over N to the NT. Temporarily, I'm going to help you understand compound interest by making a table strategy to solve this. So if you thought $10,000 1 year at 8% interest, and if you did this, if you did $10,000 times 8% interest, I get $800 worth of interest, so after 1 year I'll end up with $10,800. You'd be wrong because you're not taking the impact of compounding. It is true that if you take 8% of $10,000, that's $800, and that seems like it should be the interest, but you do better than that. So I'm going to make up a table. I'm going to put columns for time, interest, and a balance column. And again, this, you don't really have to copy this table into your notes if you don't want to, because I'm not going to do a table again. I can solve this problem with the formula really easy. So this problem says I'm going to get interest every 4 times a year, which is every 3 months. There's 4 quarters in a year. So I'm going to make a deposit of $10,000 on, we'll call it day 0. And then 3 months in the future, I'll get interest for the first quarter. Quarter of a year is 3 months. And then another 3 months after that. After 6 months, I'll get interest again. And then I'll get interest a third time at 9 months. And then my last time I'll get interest is in 1 year, and that's the day that I want to find the balance. How do I find interest? Well, interest is equal to principal times rate times time. So I'm going to use this formula. Interest equals principal times rate times time. So for the first 3 months, the amount of interest I'm going to get is the principal, the amount of money in the account, which is $10,000, times the interest rate, which is 8% as a decimal is 0.08, times the time, and I'm going to make this 3/12 or a quarter of the year. It's 3 out of 12 months, which is a quarter of the year. So I'm getting a quarter of the year's worth of interest. And it's going to be $200 worth of interest to start, because a quarter of the $800. So I'm going to go $10,000 times $10,000 times 0.08 times fraction 3 months of the 12 months. And that tells me that for the first 3 months, I'm going to get $200 worth of interest, which is a quarter of the $800. What happens to that $200 is it gets added to my account. I add $10,000 to start at the beginning of the year. After 3 months, I'm going to get $200 worth of interest. Interest is compounded, which means my $200 that got deposited into my account as interest starts earning interest. So the second time I get interest, another 3 months down the line, 6 months from my initial deposit, I'm going to get interest for another 3 months. So the balance for this 3 months is $10,200. The interest rate is 8%, but the time is still another 3 months. I'm only getting 3 months worth of interest, or a quarter year's worth of interest. The compounding interest, what happens is each successive time that you get interest, you get more interest than the last time because your interest is gaining interest. So the second time I get interest, it's going to be a little bit higher. It's going to be $204 as opposed to $200 because I'm getting interest on my interest. And that's what compounding is. So if I take the $204 worth of interest, add it to the $10,200, 10,200 plus 204 gives me $10,404. That amount will sit in there for another 3 months, and then after 9 months, I'm going to get my third interest of the year. It's $10,404, 8% interest, and this is just another 3 months. From 6 months to 9 months, the time is 3 months. So the amount of interest I get the third time, I'm going to go 10,000 times 0.08 times 3/12 of a year, and I get, I was supposed to do 10,404. Messed up here. 10,404 times 8% times 3/12 of a year, and it gives me it gives me a fraction. I need money to be 2 decimals, so I'm going to hit the SD button. I get $208.08 worth of interest the third time I get interest. So every time I get interest, it grows up. The first time I get $200, then $204, then $208.08. Let me find out my balance by adding $10,404 plus $208.08. So make it into a decimal. So after 3 interests or 9 months, I have $10,612.08. I'm going to get one more interest for my first year, and it's going to be calculated by taking the $10,612.08 that was in the account for that quarter times the 8% times the time, which is 3/12 of a year or a quarter. So I'm going to take $10,612.08, multiply it by 8%, multiply it by 3/12 of a year or 1/4 of a year. That will give me how much interest I get that last time. It's $212. It's money I have to round, so it's going to be $212.24. I round to 2 decimals for all money problems. And now I'm going to add $10,612.08 that I had at the beginning of the quarter, plus the $212.24 worth of interest I got, make it into money, so into decimals, and I come up with, at the end of 1 year, I'm going to have $10,824.32 in my account. So a terribly inefficient way to do the problem, but it's a way that I can do the problem if I didn't have a formula nor understood the formula. So I'm going to get the same answer the way that we're going to do it when we do the word problems. In order to do the word problems, I have to understand the formula and what the letters in the formula mean. The letters in the formula, the A in the formula is going to be the ending amount or the future amount of money, and that's what I'm solving for, the $10,824.32. So the A is the future amount of money that I'm going to end up with. The P says principal, but it's the starting amount of money for our class, since this isn't a business class. The R in the formula is the interest rate as a decimal. The N in the formula is the number of times interest is paid each year. And the T is the number of years. So this formula has 1, 2, 3, 4, 5 letters. And in order to solve a problem, I need to get numbers for 4 of the 5 letters. So as I read through my problem, the first number I see in the problem is 10,000. That's the starting amount of money. So that's going to be the P in my formula. So when I go to do this on my calculator, I'm going to go A equals, I'm not going to do the A equals part, I'm going to go the 10,000 part, I'm going to plug in for the P, and then I'm going to go 1 plus, because that's all from the formula. The R is the interest rate as a decimal. The interest rate is 8%. The decimal version of 8% is 0.08. So inside the parentheses where the R is, I'm going to put 0.08. The N is the number of times I get interest each year. The N is always clued into the word after the word compounded, because there's 4 quarters in a year. The N is going to be 4 in this problem. So I'm going to put a 4 for that N and a 4 for that N. And then I'm going to put a times sign because I need to multiply the N times T. And the T is the number of years, and this is 1 year. So I claim that if I use this formula, I should get exactly that answer, $10,824.32, because the answer to how much money I'm going to have in 1 year should be independent of how I get the answer. So this is a rounded answer, and my answer should round to this as well. So I'm going to do this on my calculator and show you that I can use the formula, if I understand the formula, to get the answer. So I'm going to go $10,000 times parentheses 1 plus fraction 0.08 over 4, get out of the denominator, close the parentheses, exponent 4 times 1, and when I hit equals, I get $10,824, and then something that rounds to 32 cents, because I had to round when I was making my table. I figure I'm going to have to round when I get my calculator answer. So the reason I did the problem is just so you understand what compound interest is. Compound interest is just interest being paid on interest, because I didn't just get $200 interest every single time I got interest. Every time I got interest, it grows based on the amount of interest I got the last time. I get interest on my interest. That's what compound interest is. The 2 word problems in this section are just like this problem. I'm going to do them both using the formula. So problem 28, I'm going to use the formula. I have to dig through the problem and figure out what each number represents. The first number I see is $1,000. It represents the initial deposit, so it's the starting amount of money. So when I get to my formula to figure out how much money I'm going to have in the future, I'm going to put 1,000 in for the starting amount of money. The R is how much interest I'm getting, the interest rate as a decimal. 3% as a decimal is 0.03. The N in the formula is how many times each year I'm getting interest. It's always the word after compounded, helps you figure out what the N is. In this particular example, the interest is being compounded monthly. That means every month I'm going to get interest once a month. So the N, the number of times this investment's going to be paid interest, is 12 times per year, because there's 12 months in a year. And then how much will be in the account after 10 years? The T is going to be the 10 years. So I'm going to take those numbers and plug them into the formula, so I'll be able to answer the question, how much money this account's going to grow to in 10 years. So A is the amount of money I'm going to have in the future. And for this problem, I'm going to take 1,000 and put it in for the P, and then 1 plus 0.03, I'm just plugging numbers into this formula, over 12 to the 12 times 10 power. So I just took these four numbers, plugged them into that formula, and that will answer the question how much money I'm going to have in 10 years, starting with $1,000, getting 3% interest compounded monthly. So on my calculator now, 1,000 parentheses 1 plus fraction 0.03 over 12, close my parentheses, exponent 12 times 10, and my calculator gives me an answer that I'll need to round to 2 decimals. So the answer to problem 28 is going to be $1,349.35. I rounded it to 2 decimals. The number after the 5 was a 3, so I didn't round up to 36 cents. 30 is just another example of how to use this formula in a really nice problem. So to do problem 30, I have to have that formula either memorized or written for me, so I'm just going to write it down. The formula is A equals P times 1 plus R over N to the NT power. So I deposit $20,000, get the same horrible 3% interest compounded quarterly. How much will be in the account after 17 years? So I need numbers for all the letters except one. The $20,000, because it's the beginning amount of money, stands for the P. The interest rate is 3% as a decimal. It's 0.03. The interest is being compounded quarterly. There's 4 quarters in a year, so I'm getting interest 4 times per year. So the N is going to be 4. And how much will be in the account in 17 years? The time is going to be 17. We'll plug those numbers into the formula and get the amount of money A that I'm going to have is equal to the $20,000 that I start with times 1 plus 0.03 over 4 to the 4 times 17 power. Then it's just a calculator problem. So now 20,000 times 1 plus fraction 0.03 over 4 exponent 4 times 17 power, and I get $33,242.50, and then 0.503. This 3 tells me I just leave that at 50 cents and I don't round it up to 51 cents. So my answer to problem 30, I'm just going to put a $sign and say $33,242.50 is how much money I'm going to have after 17 years. So that's from section 6.3. The only style of word problem that you might be asked is exactly this. I'm given a beginning balance. I know the interest rate and how often interest is being computed. How much money will I have at some point in the future? And that's the other word problems that I did aren't going to make their way onto the test. Not that they were terribly hard, but I know that I only ever ask from this section money problems. All right, so we're getting really close. We just have 4 sections of new material. Some of them are longish sections, so just keep hammering at it, and it's going to end quicker than you know it.